Welcome to mini lesson 1. This is the first textbook guided mini lesson. We're going to talk about definitions of temperature, and this is the first topic in the textbook, Schroeder's section 1.1. And there are several definitions of temperature given in Schroeder's book. It's interesting to ask which one is the correct definition, which one is the best definition, and my argument is that they're all correct, and each has a context where it is the best one to use. We'll start out with one that I think most people find somewhat unsatisfying, and that's the operational definition, which is that temperature is what you measure with a thermometer. So it's important that this is only circular if you imagine that you're only going to use it on paper. In actual practice, it's not circular at all, because if you give precise rules for constructing a thermometer, it's extremely practical to say that that's what temperature means, and you can use it. And you can use that, importantly, to develop better and better theoretical ideas about temperature. So actually, operational definitions are really important, especially at the beginning of a science. So an example is you could make a thermometer based on the thermal expansion of a liquid, or we note that when our intuitive concept of something being hot is satisfied, the object tends to expand. And turn that into a precise recipe for building a thermometer. So let's say put a liquid inside a narrow glass capillary like this, so that when you raise the temperature of this physical system, the level of the water rises as the fluid expands. Okay? And so you might say, you might come in with a marker and mark off units of length on this capillary and say that, okay, 1 millimeter is 1 degree centigrade, or something like that. That's what it means to build a thermometer. And then you can walk around with this thermometer and make all kinds of measurements and try to understand, what is this thing that you think of as temperature? Right? And so generally you can build a thermometer out of any physical system that has a property that seems to change systematically with your intuition about temperature. And then you standardize them and you cross-calibrate them. So a couple of examples. Resistance of a thin platinum film is a really common type of thermometer. It's called a platinum RTD, a resistance temperature detector, I believe that stands for. I could be wrong. I kind of forgot. But anyway, it's just a thin platinum film, and you measure the resistance. That happens to depend linearly on temperature between like 30 Kelvin and some high temperature I can't remember. Another way to do it is to measure the potential difference across a junction between two different metals. That's called a thermocouple. And so the idea that you can have an operational definition of temperature is sort of codified in what is called the 0th law of thermodynamics. So this is our very first law, even though it's called the 0th law. And in words, it says that the operational definition of temperature makes sense, that you can build a thermometer and you can use it to measure temperatures. The traditional way of stating the 0th law of thermodynamics is in blue here, and it says that if you have an object A and the temperature of A is equal to the temperature of some other object B, and if you also have TB is equal to TC, then you know TA equals TC. And so in math, you would probably call this the transitive property of temperature. And so it's interesting to think about that in this blue definition, the object B is playing the role of the thermometer, right? It's being used to compare the temperature of two different objects, TA and TC, right? So we start out and we somehow measure the temperature of A by touching B to it, take it away, move it over and do the same experiment with C. If this is a capillary thermometer, if the level is the same on these two, then we know that A and C have the same temperature. Okay, so it's implicit in this whole operation, that somehow we can let these two blue objects be in contact with the thermometer for long enough that their temperatures can equilibrate or become equal, I guess I want to say, right? And so there's really two special phrases in this observation. Somehow these objects have to be in contact, and somehow we have to understand what we mean by long enough. And those are important things that we're going to come back to multiple times in the coming lectures. Well, to start out, let's remark on the absolute temperature scale, right? And so what you can do is just make up any old scale you want, like, okay, 1 millimeter equals 1 degree, and call it degrees Celsius or centigrade, okay? But as people developed these scales and made more and more measurements of temperatures and the properties of materials under different temperatures, they noticed, for example, that the pressure of a gas as a function of temperature followed this linear dependence. So as you increase the temperature of the gas, the pressure also goes up linearly. But if you extrapolate the line backward to lower and lower temperature, even lower than you could ever measure at the time, you found that all the lines extrapolated to a very particular point, right? And it was the point in Celsius units of minus 273.15 degrees C. And so since this point was common to all the gases, the assertion is that it can be used as an absolute zero for a new temperature scale, an absolute temperature scale, right? And so the definition is made that minus 273.15 degrees C is the absolute zero of temperature. And the temperature scale that has the absolute zero is called the Kelvin scale. And typically you don't say degrees Kelvin. That's considered inappropriate. You just say Kelvin. And somehow the reason is that because it's an absolute temperature scale, the word degree doesn't make sense. I'm not really sure how important that is, but if you're talking to like a metrology expert, they will be upset with you if you say degrees Kelvin. And so here's more metrology. The SI Kelvin temperature scale was actually redefined in 2019 with a lot of the other measurement scales that we know about in the SI system. I guess that's redundant. SI system, whatever. So yeah, there are 7 base units, and the idea in 2019 was that you could redefine them so that there's basically one measurement that you make, which is the difference in the frequency between emission lines from a cesium atom. And then the whole rest of the system can be defined by asserting the value of certain fundamental constants, like the speed of light, Planck's constant, charge on the electron, Boltzmann's constant, Avogadro's number, and then this Candela unit, which I actually don't know very much about, to be honest. This is a unit of light intensity or luminosity, and I'm actually not very familiar with this. But in the temperature scale in 2019, the whole scale is redefined basically by asserting that Boltzmann's constant has exactly this value of 1.38 blah 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 times 10 to the minus 23 kilogram meter squared per Kelvin per second squared. Okay, you can read a little bit about this in a Wikipedia article, this redefinition that they made. So we're going to see where Boltzmann's constant comes from in chapter 2 of our textbook, and for now we're kind of just taking it as a fundamental constant that we know about from the behavior of gases. Essentially, it's defining a temperature scale. So let's make another definition of temperature. This time, sort of using our experience with the operation of thermometers to push a little bit farther towards a theoretical definition. And remember, I said we have this implicit idea that to measure a temperature, you need to let the thermometer be in contact with the thing you're trying to measure for a long enough time. And so a way to turn that into a definition is to say, okay, if you took any two objects and let them be in contact for long enough, you would expect their temperatures to be equal. And so then the definition of temperature becomes the thing that becomes equal when two things are in contact for long enough. So do you see the logical flow there? We know they have to be in contact for long enough. We assume that the temperatures become equal when they're in contact for long enough. And so we sort of invert the discussion and say, okay, if you can find a thing that becomes equal when two objects have been in contact for long enough, that's the temperature. This is more important than it sounds. It kind of sounds like I'm playing word games with you right now and trying to confuse you. I'm not. We're actually going to use this to develop really practical formulas for temperature. I think that's done for realsies in chapter 3. So what do we mean by in contact here? Because we keep saying that and we haven't really defined it. And so what I want to say, which I think will only become clear as we go on in the course, is that the phrase in contact here means able to exchange energy, right? And so our theoretical definition of temperature that's going to be probably the most important for us going forward is that temperature is a thing that becomes equal when two objects have exchanged energy for a long enough time. Okay? This will become a definition that is heavily featuring in one of these arguments we make in this course that is weird and that takes a while for you to get used to and like. There's another definition that we can state that's related to that theoretical definition, and that is that temperature is a generic measure of an object's tendency to exchange energy with other objects. So if you have a high temperature, it means most likely you're going to want to give energy to another object. If you have a low temperature, you're probably not going to want to give energy to another object. Okay? In some ways, this is almost a restatement of the previous definition in a slightly less useful way, though it actually will be useful in chapter 3 and 5. Right? And so the idea here is that having T2 bigger than T1, so a hot object and a cold object, means that this object has a tendency to want to transfer energy from itself to the colder object. Okay? And so the observation is that over time, energy transfers from the hot object to the cold object until the temperatures become equal. And so that looks like this, right? Basically, the whole thing becomes a uniform purple. And then, another important observation from this is that if you do have a temperature difference, there's a driving force for energy transfer. So why do I say that the energy transfer should go from the high temperature object to the low temperature object? That's going to come into play as we understand the second law of thermodynamics and entropy, again, chapter 2 and 3. So for now, we're sort of taking it as an experimental fact, and we'll really start to use it and understand it rigorously in a couple weeks. And similarly, we'll be able to use the theoretical definitions that I just gave you in these slides to really make practical calculations, right? And so this will all come from developing the second law of thermodynamics and the concept of entropy, which is sort of the thing that increases in the second law of thermodynamics. All right, so this is just a bunch of definitions, sort of a slow start. And in the next lesson, I'm going to give a couple more motivational slides just to try to kind of get people excited about the course. I have to tell you, this is my absolute favorite course, and I hope I can via video convey some of the excitement that I have about this material to you. So see you next time.